Okay, so to continue where Neil left off, we'll be sort of talking about tournament problems. So the name, so let me just pause for a minute and say, so while we are the best possible motivation for this problem and sort of a typical example is actually a sports tournament, because it's sort of something that we all have heard of, know about and sort of discuss and so on, but this model, okay, I'd go into the details of it, this sort of mathematical model of studying these sorts of, this problem can be used more generally for example, in election, in decision making. So, for example, if you are considering various options, you have to make a decision. Say you are a manager in a company, there are certain proposals you are considering. Each one has its merits and demerits and so on and so forth. How do you come to a sort of adopt one particular proposal and sort of discard the rest? That also resembles what we call is a sort of a tournament problem. Okay? And of course, in elections, for example, especially in systems where you have these two-tiered election systems, like in the US primary system, where you have bunch of candidates from the same party competing in the primary, and then one person gets elected from each party and they proceed towards the general election and so on and so forth. So this has a fairly broad scope of applications. Okay. Okay. So now the question, so what you heard earlier on in the earlier talk was that here is a tournament. How do we find the winner? When is finding a winner hard? And when can we easily find a winner? Or which people are likely to be the winners, right? Those sorts of things. Now I ask you even more rather more topical question. There is a World Cup going on. Your favorite team presumably is India. So if I were to ask you, how should the competition be framed, or how should it be organized so that India is the winner, like the final ultimate, that raising the cup winner, okay? So that's sort of the framework that we are discussing here. You have a favorite team or you have a favorite player, and the question is, what needs to happen as far as the organization of the tournament is concerned, so that this individual or this team is the final eventual winner. Okay, so that's what I mean by this question. How can we ensure a favorite player or team wins the tournament? Okay, so how can I even go about saying that my team can possibly win the tournament or not if I don't have some background information, right? So background information would be like, who are the other teams that they are playing? What is the win-loss record of my team versus theirs? And it's also just not enough to have the win-loss information of my team, my favorite team versus the other teams. I also need to know what the sort of win-loss record is of those teams amongst each other, because whoever wins among them might eventually play my team, if not in an earlier round, but maybe in the finals. Okay? So we have some information as to how a match between two teams would sort of play out, right? So that's what I mean by we have some predictive information about various matchups. Okay, so now this information is not perfect in the sense that whatever the history of two teams might be, one team may have lost every single match up until now and then suddenly they win. So, right, so that sort of information is never 100% perfect. It's predictive only, and usually in real life instances these are modeled by probability scores, like the probability of this team winning against this team is this, and therefore the probability of the opposite situation happening is 1 minus that value. And so the point is that if I have a team, if the favorite player that the team that I'm supporting, in this case I'll be using the word favorite, if it could beat everybody, okay, it happens sometimes in, it's like, let's just continue with the sports analogy. So in sports, there's one dominant team, it beats everybody, so like you're in good shape. If that's the team you're supporting, great, chances of winning very high. If you're not supporting that, too bad, you're most likely not going to win, right? Now, but is that really necessary? It turns out, what do you think, is that necessary? No, right? Why? Anybody take a guess? You heard like there were lots of like the reasons were sort of discussed in the previous talk, but you can also guess like just by experience, like if you have watched any sports tournament ever, you would sort of have an idea. So the basic idea is, if my guy, I mean like the team that I'm supporting only plays teams that it can beat, then I'm in good shape, right? As long as if there are teams that my team cannot beat, but that team loses to some team that my team can beat, then I'm fine, right? I'm in good shape. As long as I don't have to play a team, my team does not have to play a team which I cannot beat, that's the hard situation. So basically, if I can rig the tournament in a way that my team never has to play a team it cannot beat, then my team can actually win the competition. That's literally a sufficient reason of winning the competition. So when I say what can I do? What I mean is the organizers. So who would do all these things? It's the competition organizers. And you may ask, why are they doing this? Well, because many a times actually in real life situations, these things matter because they want to increase viewerships, right? They want to have the teams that attract most attention are the ones that the organizers would want to feature in the final. There's a famous, so currently if you see, I wanted to run some examples and I wanted to use the Cricket World Cup example, but the problem was that this time around there are fewer teams, there's a huge round robin sort of thing going on, and there'll be only 2 knockout rounds. So the examples were not, I mean, the situation becomes only 4 teams will be basically competing in the knockout situation. So in my example, in this particular talk, what we will be talking about are knockout tournaments, meaning you lose one game and basically you go home. Okay, so there are no round robin situations that you can make up your sort of score eventually. So the best possible example is probably the FIFA World Cup, the Football World Cups, where they have like at least 4 sort of elimination rounds and so on. So I don't want to spend a lot of time in this example, but what I'm trying to emphasize by this is that who you play actually matters. And who you play is decided by what is generally called a seeding or a bracket. Okay? So Neil mentioned the concept of a seeding. It's basically, I will sort of explain it in the manner that I would need it for my talk, but basically let's just see this example a bit and you'll know what is going on, okay? So this round of, can you see this? So these were the teams that qualified for the pre-quarter final round, okay, during the last World Cup. Like some weird things happened in the last Football World Cup. England, I think nobody expected it to reach semi-finals, like even the ardent football fans, but they actually managed to get all the way to the semi-finals. Why did that happen? Because in each round, beyond the pre-quarter final round, they actually played a team that they could beat. Okay, so first they played Colombia and England. They beat them. Well, there was a close match. It was a penalty and so on. Then they proceeded to the next round where they played against Sweden. So what decided the fact that England gets to play Sweden in the next round? If, say, for example, if you look above, if England played Brazil or England played France, maybe the outcome would have been different, right? So in each round, who you play will matter, right? And not only that, who your other people are playing against each other, because that matchup decides who will proceed to the next round that you will play against. So all these things, all these sorts of details are basically determined by what we call the seeding. So the precise notion of a seeding, definition of a seeding, might vary from competition to competition, okay? So this was originally used in tennis. Tennis is a classical sort of knockout tournament. Every round is a knockout tournament. You get to play one round, you have to win it, or else sort of you go home. So it basically describes the path any player has to take, all the sort of the path, meaning who all he might play, all the way to the final, right? So, and this is sort of, as I said, is specific to the tournament. So in our setting, what we are assuming as a seeding is basically a permutation or an ordering of the players. You understand ordering, right? Yeah, ordering of the players. So let's say V1, V2, these are the V8, there are these 8 players, okay? This is the way I will interpret the seeding. And this is sort of kind of important for this. So please pay attention. If you don't understand, please ask me, okay? So in the first round, V1 and V2 play each other, okay? They are just sitting in consecutive position. The next match in the first round, okay, so say V1 and V2 play each other, V1 wins. So V1 proceeds to the next round, okay. Next, the second match of the first round is between V3 and V4. So between V3 and V4, let's say V4 wins the match, and so V4 proceeds to the second round. The next match of the first round is held between V5 and V6. V5 wins and proceeds to the next round. And eventually, V7 and V8 play, and V8 proceeds to the next round. So the second round will be held between V1, V4, V5, V8. And now again, this is also a seeding, I'd say. This is basically a seeding for the second round. Why? Because in the second round, V1 will be playing V4. And V5, and so suppose V4 wins, so it moves to the next round. And the second game of this second round would be played between V5 and V8. One of them wins, okay, V5 wins. And now the final is when you have only two teams left. And so, for example, here V4 and V5 play each other and V4 is the winner, right? So this is how I will interpret the sort of seeding. Okay. So if I asked you, what would it take for my team to win the tournament? What am I basically asking? Given the information I have about the various matchups between teams, like suppose I have information as to who will win against whom if two teams play against each other. Now, what I'm basically asking is there a seeding which will ensure that my team will go all the way to the finals, and then in the finals will play against a team that it can beat, right? That's basically what it translates to. So that's the question basically that we are asking. So, and this is what is known as tournament fixing in literature. It's basically modeled by a directed graph. Do you know what a directed graph is? It's a graph where the arcs have directions, okay? So it's undirected graph is one where the arcs do not have direction. So for example, this is a graph on what, 8 vertices? Yeah, 8 vertices. So this is my team, okay? This is my favorite. Okay, let's see. It's my why is it green? Okay. Okay. So this is the favorite. So these are the 8 players. So this directed graph basically gives me the information as to who will win against whom when certain two players play against each other. So just looking at this, if B and C play against each other, B wins, okay? This directional arc, arc between B to C means B wins against C. So between A and B, can you tell me what it means for this? How do I interpret this arc? Very good. Okay, so this is the sort of convention we will be following. So this is what we'll call the win-lose graph. This is the information I have. This is the predictive information we have about various matchups. So the question now is, by looking at this win-lose graph, can I extract a seeding, okay, that will ensure that this star player, this favorite guy, will actually win the tournament. Okay. So this was a question that was introduced by these 3 people way back in 2009 in a paper that appeared in AMAS. So, okay. So the question now, the first question is, can I solve this problem, right? So that's what I mean, like how hard? Is it like, is it obvious? Do you know sort of can you make a guess, or like, do you have any opinion as to what this should be? Like, should this question be easy to answer? By easy, I mean like in polynomial time. Say, like, take a guess. Well, it turns out, if I said we need, seeding is an ordered list, right? So if there are n players, I might actually have to try n factorial many seedings, right? That's like the most I would have to try. I try all possible things. I see each time I sort of run the tournament, see who wins against whom in each round, and see whether there's any way for my team to win. If I find one of them, I'm done, right? So the question is there just because there are n factorial seedings, does it mean I actually have to cycle through all of them and check? Maybe there's an efficient way of finding, of sort of looking at just the sum of them, or some other way, altogether different way to know whether there's a way for favorite to win the tournament. So it turns out that we don't think there is an efficient algorithm. Okay, so I say we don't think is because we still don't know whether P is equal to NP or not. So this is what we call an NP hard problem. Okay, generally speaking. Now I am sort of giving out the sort of final plot line a little ahead of time, but if you remember that in certain cases, can you tell if it is ever solvable in polynomial time for restricted cases? In worst case, maybe it might not be solvable in polynomial time. But can you think of any special cases in which it can actually be answered in polynomial time? Sorry? Yeah. Okay, very good. Why is that? Right. So is it clear why I have to play, like, so you're saying my guy has to play log n rounds to win the final tournament, right? That many now. So therefore it has to be able to beat at least one person in each round. So I need to be able, yes, that's actually true. If I look at the graph and see my guy does not beat log m people, then it's like you can say that there's no way you can find the thing. But anything else, any other condition? So there are these notions of these powerful players, right? The super king, high degree super kings, so on and so forth. So if your team satisfies those properties, then it might be able to win. Then it would be able to win. The question is, can I now find a seeding? Just answering the question yes and no is one thing, but then if you need to find the seeding, which will actually ensure that they win, that's like a different question now. So the point is that while in general it might be hard, this question to answer, this whether there exists a seeding, which will enable my favorite player to win, in certain special cases, this might be easy to solve. Okay? All right. So if that graph that we saw before, that win-lose graph, if that graph is acyclic, doesn't have cycles, can then I say that, okay, then can I answer the question? Anybody, please. Just take a guess. So Neil sort of mentioned this, like it was somewhat towards the second half of the talk, maybe so you had dozed off a bit or so on. So when it requires a proof, it's just not maybe obvious, but the point is if there are no cycles, there are these vertices, there is a vertex, and okay, remember in that graph, there was an arc, there was an edge between every pair of vertices. Because the thing is that you have information as to what would happen if any of these two teams play, right? So there is an arc between every pair of vertices. In that sort of a graph, which does not have a cycle, there is a notion of a source, okay? A vertex which does not have any incoming edges. So that vertex will win the tournament. That vertex is the unique winner of the tournament. So if your favorite player is that vertex, then there exists a seeding. If it is not, then there's no way your team can win. That's the bottom line, right? Okay. So that's why we say that if the win-loss graph is acyclic, this is easy to decide whether there exists a seeding which will ensure your favorite team will win or not. You basically check whether your favorite team is the source vertex in that graph. Okay, so in general it is NP hard, and so we try to, so if a problem is NP hard, do we just give up? Like, I mean, this is a very important question. There are sports betting is a sort of a huge industry. I don't know, maybe you don't participate in that sort of thing. It's increasingly becoming legal around the world. It's a big industry. These problems actually need to be solved. There are people interested in and so on. So we want to find we want to find an answer as best as we can. So there are various proposals as to what we can do, what kind of algorithm we can hope to find, right? So if I told you that in general the algorithm would be exponential time, right? However, suppose I'm able to give a time, I'm able to construct an algorithm which has a time complexity of the kind where, let's say, it is exponential in some function of k. So this is an exponential function, but polynomial time. So the time complexity of an algorithm is, let's say, something like this. Okay, so this is the time complexity of my problem. So n are the number of players and so on and so forth, where this value k is significantly smaller than n. So when I say significantly small, what I'm trying to say is, let's say, constant. In most, if I told you that, okay, this is the time complexity of this algorithm, in the worst case, k can be as bad as n. But for most reasonable situations, k is very small, almost constant like when compared to n. Then this algorithm, for all those practical purposes, basically works like a polynomial time algorithm. Okay? So this is sort of these are the types of algorithm that we are now interested in. Because we cannot solve the problem in sort of polynomial time in general, so this is sort of the time complexity that we are aiming for. Is it clear? Any questions? Okay. So does this match with what what you would consider as a reasonable goal? Like, is this what you would think of doing if you are faced with a NP-hard problem? So what this value k is, I have not said anything, right? I just generally said, like, suppose I could tell you that I'll give you an algorithm which will work like this. This k is some value which is significant, then you'd be happy. So I'm saying what could be that k, right? Suppose k is the number of upset matches in the tournament. What is an upset match? Upset match is one where a lower ranked or a lesser team beats a higher or a better team. Okay? So usually, in most cases, upsets happen rather, compared to the number of matches that there are very few upsets, right? There's a reason why it's an upset, because you don't expect a lesser ranked player or a lesser team to beat a better team. So this is why we have zeroed down on k, because we expect this, if I take k to be this, then it is likely to be much smaller than n. Okay, so we define this parameter k formally to be the number of pairings in which a player will beat a better player. So how do I define a better player? Can I formalize this notion mathematically? What it would mean to be an upset game, what it would mean to beat a better player, and so on. Do you have any proposals? Like, do you, sorry? Correct. So that would be an example of an upset match in a real life situation, like in a tennis thing, right? This 15-year-old tennis, she beat Venus Williams in the first round. Like, this is a grand upset. So, and she qualified. So that's the example. So, but mathematically, how do we define who is a better player? How do we define, if I knew what a better player would be, is I can say what an upset is, right? A player beats a player who is better by my definition. So how do I define a better player? Any suggestions? Okay, so do you know about this thing called topological ordering? Have you heard of it? Okay, so what happens is this. In this graph, okay, this is the win-lose graph. I look at the set of cycles. Now, I'm not saying I'm finding the set of cycles, but suppose I knew what the set of cycles are, okay? Now I tell you that I give you a subset of edges in this graph such that by removing those edges, okay, the graph becomes acyclic, okay? Do you understand what I said? So, but by the way, remember, if I just delete those graphs, then I no longer have a win-lose graph, because a win-lose graph must have edges between every pair of vertices, right? So suppose, so instead of deleting those edges, I just switch their directions. So I tell you that it is no longer it does not have any more cycles, right? So then can we say something? So remember, we said that when I don't have any cycles in a graph, that's the easy case. That's when I can decide right away whether there exists a seeding or not, right? So I'm telling you that suppose there is a subset of edges whose reversal, like I just switch the edges, gives rise to an acyclic graph. Then can I define the notion of a better player? Like what means to be a better player compared to somebody else? Okay. So let's move forward. So given the graph like this, okay, after switching these edges, I perform what is known as a topological sort. Okay, so I get a ordering on vertices. This ordering of vertices has this fantastic property that all edges will go forward. By that, what I mean is all edges are pointing from left to right. So it's an ordering from V1 to Vn, whatever the vertex labels are, where there is an edge between directed edge between every pair of vertices, and all the edges are pointing from the lower to the higher. So what do these directions indicate? That by lower I mean the left player beats the right player, right? Remember our convention of arcs. The team that is on the left hand side will now beat the teams on the right hand side. So this is sort of what I give you. Now the edges that I had originally reversed, okay, those edges whose removal will basically make the graph acyclic, I gave them a special name, call them the feedback arc set. Okay, just like bear with me. So this is just a special name, why it is and so on, so that's like beside the point. So now I basically switch back their edges, back the direction. So I have the ordering, all the edges are pointing left to right, and now I go back and switch the ordering of those edges that had initially changed. So now what do I have? I have the same ordering. Most of the edges are going, let's say, from left to right, and in between there are these edges which are pointing backwards. Correct? That's how it looks. Okay, I think I have a picture. Yes. So this is an example. Okay. So I think this is actually the topology sort of, I mean, after sort of, I figure this is basically what would happen if these were the feedback arc set. So these red edges are the ones whose deletion will lead to an acyclic graph, or whose directions, if you switch, would lead to an acyclic graph. Okay. And so after performing the topological order, initially these edges were pointing forward, left to right, and so on, but then I switched back the orders and I highlighted them with red color so that it's easy for you to notice that all the edges, so there are lots of edges missing because there would be edges between, let's say, B and F and so on and so forth. So whatever the edges that are missing, they are basically black edges, meaning going from left to right, and these red edges are the ones that are going from right to left. Okay. So this is basically the ordering. Now what can I say? Now using this ordering, I want to say that A is a better player than B, because A appears to the left of B. So besides these red edges that are pointing back to A beats all the other players. Correct? So the only player that A does not beat is F. So B, the only player, the two players that B does not beat, the one that is sitting to the left of B, that is A, and my favorite player, this team, right? And then C basically does not beat any of the teams that are sitting before it, A and B. Obviously, they are more better players than them. And C is not beaten by any of the players to its right, meaning C beats everybody who is sitting to its right. So C is better than my favorite player. C is better than than E. This edge is missing. This would be a black edge. C is also beating F, and C beats G, C beats H, and so on. Okay, so this is how I interpret better. So these red arcs are the upset games. What does upset games mean? It means that in my tournament, if F were to play A is a very powerful player. See, like it beats everybody except F. Then if there were to be a matchup between A and F F would win. Okay, so this is the information I have at hand. So this, so the size of the feedback arc set is that parameter k. So for your purpose, you can remember as the number of upsets. Okay, so that is my parameter. So because I expect the number of upsets in a tournament to be considerably smaller than the number of matches played, so that is why I can hope for a time complexity I wish, which is exponential in k but polynomial in n. Okay, all right. So now I am formally going to state this question as the input is a win-lose graph. The question is, does there exist a seeding that ensures that your favorite team wins? Now, implicit in this is, suppose you know what those upset games are, upset matchups are. Usually, in a general setting, finding feedback arc set of a graph, of a directed graph, it is also an NP-hard problem. Okay, so I can't just find that feedback arc set easily. But given the time complexity that we are hoping for, I can show you that actually I can find the feedback arc set separately, and then I assume that I have it at hand, the upset games, and using that information, so implicit here is assume so FAS is that sort of upset game stick. Okay. This is the question that I'm asking. So the known result, the first result that was suggested was n to the power k. Okay, this was the first algorithm that was suggested. Followed by that, so this is an example of how people keep on, you have one algorithm but you're not happy with it. You keep on making improvements to that and showing a better and better time complexity. That's usually how sort of this algorithm research goes. Okay, so the second proposal was to give an algorithm which is exponential in k, right? It is 2 to the power k squared log k, but polynomial in n. Do you agree that this is a better algorithm than this, or maybe not? Why? Like, why is yeah, please. Okay, good. So here the exponent of n, if you want to call it that, would be some constant value, like 2, 3, 100 million, all those things are a constant value, right? Even if it is very large constant. Here it is still k is still a variable, correct? So this function is a faster growing function than this thing. This, if I just look at the polynomial dependency, right? So this is a thing. Now, is this a good enough? Yes, it is actually pretty good, because if k is very small, this is actually not a very smallish function of not a very small polynomial, but okay, this is polynomial, and this is sort of 2 to the power k squared log k, right? So not recently, maybe a year or so ago, we improved this to some of my co-authors and so on. We improved this to 2 to the power ordered k log k. So the improvement is from this k square to this sort of a single k. Do you see? So this is just not to emphasize on this much, but just to notice that these are all sort of step-by-step improvement on the same problem. We are solving the same problem, but the time complexity, time taken to solve the problem is getting better and better. Okay. So now I want to sort of discuss a bit about how this algorithms proceed, specifically the last one. Okay. So at the heart of these algorithms, the last especially, is this combinatorial property known as spanning binomial arborescens. Okay, arborescens is a fancy name for, let's say, forest. So this was the win-lose graph. It has order n square edges, correct? From here, my problem, I will tell you how, but translates to finding a subgraph of a very special structure. Is it clear what I am saying? So this was the graph given to you. This tells you all possible matchups, right, between teams. Only some of these matchups will actually occur in the real tournament. And that's the one that I'm trying to control, to have matchups which will be so that my player never has to face a team that it cannot beat, right? So from this graph, we are trying to find a subgraph with some special properties. If such a subgraph exists, I'll define what the subgraph is. Then I can say that there exists a seeding which will ensure that my favorite wins, okay? And it's an if and only if condition. If such a subgraph does not exist in this graph, then I say that there is no seeding which will ensure that favorite wins. Okay, so the spanning binomial arborescence, I'll call it SBA from now on, because the word is kind of a word, this term is a bit wordy, and so on. So this is how we basically define. So these are the vertices from this graph. I just extracted them out, okay? I just wrote them in this sort of, I wrote this at the top because this is my favorite guy. I want this person to win. So between these players, there will be some games, right? So imagining that everybody plays in each round unless they lose. That's the format. So it's not that case where some players have a bye in the initial rounds, like the kind that Neil explained. Here everybody gets to play a round until they go, like, lose and go home. So therefore, I'm trying to find the first round matchups so that the people who win the first round will obviously go on to the second round, then again define the matchups in the second round, and so on and so forth, so that eventually only my favorite team wins, right? That's the agenda here. So from this, I'm basically trying to find edges from this graph. So let's see. So imagine that so if you look at it, I have colored them. I think you can see these are sort of what, yellowish color edges. So between F and A, this is the edge that I picked out, right? So I'm saying the first round F will play against A. Another first round matchup would involve E playing against H. This is this thing, this edge. The third matchup in the first round would involve B against C. Okay, so this is the B against C. And the final first round matchup would involve favorite playing against G. Okay, so then it means that F wins its matchup, E wins its matchup, B wins, and obviously favorite must also win, right? So then these people go on to the second round, correct? F, E, B, and favorite. So for the second round matchups, again I'm looking for how to, well, maybe favorite could play B, or favorite could play E, or favorite could play F. Why did I choose that favorite should play B and E should play F is the thing that decides that whether favorite will actually eventually win the tournament, okay? So suppose I decide that E will get to play against F and favorite will get to play against B. So then these are the edges. These are gray colored edges. It's marked here, these edges. So this to B, and this is the other edge, okay? These are the second round matchups. And then it means that E wins its matchup against F and favorite wins against B, because that's what my win-lose graph tells me. And then the final round is between a favorite and E. And over here I can see, well, see this edge between favorite and E, favorite actually beats E, so favorite is actually the winner. So this whole thing is to basically find a subgraph like this. So you agree this is a subgraph of this graph, because I picked out these edges from this graph, right? So all the vertices are, the vertex set here is exactly the same as this. This is why it's a spanning subgraph, because all the vertices are part of this subgraph. And these properties, how I sort of pick these edges, they have some more special structure, but basically I'm looking for a rooted tree, spanning tree, where the root is favorite. So the question is, does there exist a rooted tree in this win-lose graph where the edges are all pointing downwards, the root is favorite, okay, and some more additional properties are satisfied? Are you still here with me? Okay. All right. So this is what we call an SBA, okay? So let's define the binomial arborescence, what it means, okay? So an unlabeled binomial arborescence is a rooted tree at V, okay, and it is defined recursively. So a single node V is a sort of tree in itself, right? It has just one node. So this is called, it's a trivially a SBA, it's a binomial arborescence. So now imagine I have a situation where I am going to tell you the definition. I have two trees, okay, the size is not the same here. It is important that the size is the same. Again, I've managed to make this somewhat bigger, but okay, you get the picture, okay. So these are the two trees, okay. So the root is say U and V, okay. And now I say these are the two trees, I will create a bigger SBA, okay. I'll create a bigger BA, binomial arborescence, involving these two, using these two trees. I basically can add an arc between U to V or V to U, whichever direction I want, and I have basically created, sorry, this one says, it should, what is going on? I'm new with this particular technology, so you'll hopefully forgive me if I'm clumsy. So this is now an SBA with double the size, right? So this is now a tree which has, whose size is this, the number of vertices in this tree, and the number of, plus the number of vertices in this tree. I started out by saying they are of equal size. So basically this has twice the size, right? And here the root is basically V. See, I said all the edges have to be pointing downwards. So when I started with this smaller SBA, V was the root, meant all the edges, sort of all the edges are going downwards. So here, by merging these two trees, I've created a bigger SBA where V is the root and U is one of its children. These are the other children and so on. And so this is a bigger SBA. This is basically how we create a binomial arborescence, recursively defining. We always take two binomial arborescences of the same size and sort of give an edge arc between the roots of those two things, and thereby creating a bigger tree. Okay. By doing this, if I manage to cover all the vertices in my original graph are part of this, then it's a spanning thing. The notion of spanning only makes sense when there exists another graph of which this is a subgraph. So here there is no notion of a subgraph, or there's no other bigger graph, so I'm just calling it a binomial arborescence. Okay. So now the edges that I'm using to define these arborescences, this binomial arborescences, if they are part of a directed graph, okay, where the vertices actually obviously have labels, right, then what I get is a labeled spanning arborescence, spanning binomial arborescence. So the labeled portion comes from the fact that the vertices actually have labels. They are not the, when I was merging them, the roots actually had identities specific, and I took them from a bigger graph, and all the vertices of that graph were present in this binomial arborescence, and that's why it is a label spanning binomial arborescence. Any questions? Do you understand how I created this thing? Okay, so just the intuition of this is, what's happening is, maybe I can go back a little bit. Yeah, so what's happening is, what this means is, imagine the tournament was held between players that are part of this subtree. Then what I'm saying is, if these are the matchups, like the way I defined before, this is the way if the matchups were held in that competition, V would be the winner. Similarly, in this subtree, if I look, if I have a tournament involving the vertices in this subtree only, then U would be the winner. And then what I'm saying is, V and U, now I merge these two sub-tournaments, and V and U basically play in the finals of these tournaments, and V beats U, therefore V wins this combined tournament. That's the intuition behind the SBAs, okay? Okay. All right. So tournament fixing, the problem that we are interested in, is basically is equivalent to solving this particular problem involving SBAs. Does the win-lose graph have an SBA spanning binomial arborescence, okay, where favorite is the root? That's basic. So this is the question. This is the combinatorial question we'll be. So solving this would require us to solve this, and vice versa. Okay. So okay, this equivalence was shown by some people like in 2010 and so on and so forth. Okay. So here we basically are given the win-lose graph, and now we are basically looking for a subgraph, a spanning subgraph, where the subgraph is a rooted tree and the root is favorite. That's the question we'll be talking about now on. Okay. So just before I go into the algorithm, I'll just talk briefly about the properties of SBA, some more properties of the SBA, sort of they are important, just so you, you can follow the arguments forward. So for every vertex V, okay, so B is, let's say, an SBA, okay, so this is this tree, it has some sort of a root, it has all these children, all these edges are pointing downwards, these are the subtrees rooted at its children and so on, okay. This is the sort of, this is, let's say, the how it looks roughly. So this is the vertex V, okay, this is, say, this is the whole tree B, and the subtree rooted at V is called, say, let's say, B of V, okay, this is just a notation thing. So this, as we said before, this subtree itself is an SBA, right? It's an SBA in what? If I took that win-lose graph and just restricted, only looked at the subset of vertices that are part of this subtree, okay, and looked at the induced subgraph, then what I get is a smaller win-lose graph involving only the vertices of this subtree, right? So within using that smaller win-lose graph, if that is the win-lose graph I am looking at, then this subtree is an SBA in that win-lose graph. Similarly, I can say that this is, say, some other, by the way, these vertices are obviously disjoint, like they don't share vertices, right? This is sort of one vertex can only appear once in any one of the subtrees. So same thing holds for U. If I look at the vertices that appear in this subtree and I look at the subgraph, if I look at the win-lose graph and look at the induced subgraph of these vertices in that graph, what I will get is a smaller win-lose graph, and this will be an SBA in that subgraph. Okay, so that's sort of happening here. Furthermore, the number of vertices in an SBA is always a power of 2. So that's why I wrote this. Okay, this log n is an integer, this whole value. N is always a power of 2. And each of these subtrees, the size of the subtrees are also power of 2. Okay. Now, a root of an SBA, that if that SBA has n vertices, as is the case with B, then that root will have log n children. Okay, you can label the vertices from V1 to V log n. This is what this is, and the sizes of the subtrees rooted at those children sort of increase by a sort of a factor of 2. So one child will have no subtree, like that's the only vertex. So the first one of the vertices of this root will be just this. This is the subtree, one vertex subtree. The other child would be an edge, basically, because this is a subtree on 2 vertices, right? The other child would have a subtree on how many vertices? If you're following this formula, what should be the size of this subtree? So this is size 1, which is 2 to the power 0. This is size 2, which is 2 to the power 1. What should this be? Size 4, right? So as I said, this should also be an SBA of 4 vertices. So how should it be? It should also have this property that this has one child of this kind, the other one is a child like this. So basically, this guy has one child who has a subtree rooted at it which is of size 1, another child which has a subtree rooted at it which is of size 2. So this is how it will be, and this is how it proceeds. This is what this relationship says. Okay, so these things are very essential, critically used in our algorithm. Like this is a lot of structure that one can exploit. Okay, so the algorithm proceeds in several stages. Okay, because our agenda, remember, is to solve this question in this much amount of time, I can actually take exponential 2 to the power k log k time to actually this is the time. So as far as k, remember, is the number of upsets, right? So if I knew the number of upset games, I can essentially use exponential amount of time to figure out the relationship between those vertices. If I knew the set of players who are participating in those upset games, then this time complexity basically tells me, it's like a clue that, okay, then I can use exponential amount of time to figure out the relationship between those players in this SBA. if such an exists, right? That's what I'm going to do. So first step would be to guess something. By guess, what I mean is basically I will try all possible things, all possible ways of doing something, and I'll explain what this formally means. And if there exists an SBA in which my favorite is the root, then as I enumerate those sort of structures, then one of those guesses will basically be consistent with that hypothetical solution. That's what I mean by a guess. So I enumerate a bunch of things, and one of those things will basically lead to my solution. Second step would be to verify. Let's just go back a little. To verify. So as we saw before, this is why I sort of explained those properties before. If I just try all possible guesses, it cannot possibly lead to an SBA, because SBA has a lot of sort of very structured properties, sizes, path lengths, and this and that. So basically, when I'm guessing these things, for each of those guesses, I should basically verify whether those guesses, because I'm doing independent, I'm guessing things independently, I'm trying all possible things, so I should basically check whether all those guesses can work together to actually generate an SBA. So that's this verify step, okay? So most of the guesses will be ruled to be infeasible, like they cannot possibly be part of an SBA, so we basically get rid of them. So this is a cleaning up step, okay? And the third step, so all those guesses, like the ones that we sort of get in the first step, which go through the second step, will move on to the third step. So here, basically, we will use a greedy strategy to fill out the information that is missing from step 1 and step 2. Okay? So here, because of this guesswork, here we'll take exponential amount of time to sort of exponential. Always remember, this is the sort of target. So I can take feasibly this much amount of time in the first step itself, as long as I don't exceed this much in step 2 and step 3. Okay? So that's how we will proceed. Okay. So what do we guess? Basically, what we guess is the relationship, roughly speaking, between those players which are part of that upset games. So this is what I call the template of that. So imagine that there exists an SBA, there exists a tree rooted in the favorite, a directed downward tree, and I'm basically trying to find that tree. Okay? There exists such a thing, I don't know what it looks like, and so on and so forth. I know the set of players that will participate in, if they play against each other, that there will be upset games, like the lower ranked team will beat the higher ranked team. Okay? So using that information, I basically guess the partial structure of that SBA, where the paths, certain paths will be sort of compressed, so it's like a those edges and add vertices to it, and then it will resemble the actual SBA. Okay? So that's what this is. So I guess a compressed tree. The second information that I guess is the relation. So do you know what is least common ancestor is in a tree of 2 vertices? In a rooted tree, do you know what a least common ancestor is? Okay, so we'll sort of go. So let's just take this for a moment, that we also guess the position of the affected vertices. So the affected vertices are the ones that are basically participating in those upset games. Okay, this is just another name. And the position of their least common ancestor. So I look at every pair of these affected vertices and see where their least common ancestor might be. I have no idea where they would be in the real actual tree, but I sort of try all possible things, and then I generate all these sort of templates by doing that. And also I guess is the length of path between these upset games. So if this is my sort of, let's call it, this is favorite, because this is the tree I'm guessing, root will always be favorite. Say this is, what was that? Okay, we'll run into an example. So this is, say, AB. This is this thing. So this is sort of the type of structure that I'm guessing. I don't know whether, I don't know yet whether in the eventual SBA that I'm trying to find, if A and B are actually playing this edge, direct edge would mean that they're actually playing each other. But I don't know whether that will be the case. I will actually guess all possible situations in which maybe A does not play against B, but there are few other teams that they play against. So meaning A plays against, say, A1, A1 plays against A2, and so on, and then eventually as I go down this path, the last person in this path gets to play against B. Okay? So all I know is A has this sort of structure tells me that A has proceeded to a round higher than B as well as C. So this is sort of the information I guess in the first round, in the first phase. Okay? And these length of these paths are also guessed. And there are subtrees that I suppress. So these subtrees, okay, they do not contain any upset games. These are vertices that do not participate in any upset game. They always lose to higher ranked players. These, I have no information about where these vertices exist. All I am doing is guessing how large the subtree rooted at B would be. Similarly, I also guess how large the subtree rooted at C will be, and so on. Next step is sort of this thing that all these guesses, they satisfy the SBA property and so on. And so if it does not, we basically discard that guess, and so we move on to the next step. So in the last step, that guessed structures that we did, like these were these paths that I guessed, let's say length AB, A pointing down to B. I will try to, this basically tells me that there are this many number of internal vertices. Let's say there are 5 between A and B in that hypothetical SBA, right? The one that I'm actually trying to find. So I will have to find 5 vertices which are not part of that upset games, the unaffected vertices, and add them to this. This is what I do in the third step. Similarly, the subtrees that I have suppressed underneath B that do not contain any upset games, I also fill them out because I also know the size. I have also guessed the size of this subtree. So these are the all the missing information I fill out in the last step. Okay? All right. So how am I doing time wise? Another half an hour. Okay, that's sort of okay. Yeah, you were asking a question. Correct. So yeah. So yes. Not acyclic sub-tournament, an acyclic tree, sub-tree. Yes, yes, yes. Yes. It need not be. So yeah, so that sort of thing. So how far, so the interval around B is what these lengths tell me in a way. So what this is suppose A and B are those affected vertices, meaning these are vertices which will be part of some upset games, okay. I don't know whether I'm not saying that A and B will play against each other and therefore B will beat A, that's not what I'm saying. I'm saying A and B are part of some upset matchups, okay. So either A will beat a team which is ranked higher than it, or it will get beaten by a team lower than it. The fact that in my guessed structure, this template, I have guessed that A sits above B, okay, in that SBA, and the length between A and B is 5, okay, tells me that in that, I'm telling you ahead, basically this is what you can expect, that in that topological order, okay, if A sits here and B sits here, okay, then the vertices that sit between A and B, which are not part of the upset matchups, they will be used to fill up these this length. So therefore, the question she was asking, that's sort of the intuition that when you know these affected vertices, where they are placed, that sort of tells you what is the sort of the ball around them that you should look for players to fill out these things, these in between matchups, right? So that answers your question. So that's what will happen. The reason the greedy works is because those sorts of properties actually hold for this, okay? So one has to prove that those things happen, but they do, and that's the sort of the proof of correctness of this greedy strategy. Okay. Yeah. Oh, thanks. All right. So least common ancestor and closure of the least common ancestor. This is a very useful concept. So it's like if you understand this and like try to use it in some other place where you find it useful. Okay. So here is a tree. Okay. This is an SBA. Okay. So okay, not SBA. Say it's a rooted tree, right? This is the root, and all these arcs are pointing downwards, and so on. Okay. So the set X. Can you see the colors? Oh no. I don't think, can you see the green? These are colored green, okay? Is it clear that some vertices are colored green, others are black? So these are the X vertices, okay? So among these two vertices, if I say who is the least common ancestor of these two vertices in this tree, would you know who that would be? This vertex. So an ancestor is a vertex that appeared in the path from the root to me. So I look at this vertex and I look at the path from the root all the way down to this. So that is this path, right? Can you see? Yes, I think this works as a this sort of a pointer. Okay, so in this path, each of these vertices are sort of its ancestors, right? So now if I look at the same sort of a path from the root to this vertex, this is the path I have. So these people are also the same. This guy and this guy share all the ancestors, like they have the exact same ancestors, right? So the least common ancestor is the ancestor that is closest to them in terms of the level. So in this case, this is the least common ancestor. Now if I say this vertex and this vertex, who would be the least common ancestor? This one and this one, can you tell? Who would be the least common ancestor of this guy and this guy? There are no labels here, but you can point something. Parent of this guy? So this one? Yes, exactly. So if I again look at the path from the root to this guy and root to this guy, this is the common portion of the path ends here. So this is the least common. Least meaning the person who is immediately above us, who is both of our ancestor. That's the notion. Okay, least common. There's a common ancestor and the who is closest to us. Okay, so doing this, so I'm going to find the least common ancestor and I'm going to define a closure set for this, okay? So I basically copied the same thing here, and so pair of vertices by vertices, we'll just run through this. So between these two vertices, this is its least common ancestor. Now, next step, now this set is part of my X prime, okay? So this vertex was not originally in X, but the moment I find the common ancestor, I add it to my set X, okay? So I'm growing the set X. So this is a common ancestor which was not originally in X, and I add this to X. So now between this vertex and this vertex, who is the common ancestor? This is the least common ancestor. This is also not part of the original set X. So I add this to X as well, okay? So that's what I mean. So now next is what happened? Yeah. So now notice between this vertex, so I'm still in the subtree, let's imagine. So between this X vertex and this X vertex, their least common ancestor is this. It is already present in my X set. So I don't have to add anything, correct? And between this guy and this guy, this is the least common ancestor. So basically this is the least common ancestor both of pair of this vertex as well as this. So I don't have to add it. So this part of the tree is over. Now I move on to this side. So between this guy and this guy, who is the least common ancestor? Actually the root, right? Because that's the sort of the only part. They do not have a common edge sort of in the root to the vertex path, and so this is the only ancestor they have. Now this vertex was not part of the X set, so I also add this to the X. So this larger x, okay, x union some of these additional common ancestors which were not part of the original set is known, what we call the least common ancestor closure, okay, LCA closure set. So this is the closure set, okay, all right. So we know, it can be shown quite easily that if you have a tree, rooted tree, say T, and you have a subset of vertices, okay, in M is a subset of vertices, okay, then the least, so instead of M you can say X, I don't know why I used M, then you can say that the set of the least common ancestor closure of X, the way we describe this, can only be at most twice the size of X. So this property, okay. And also any subtree you find, okay, in this graph where basically you have the tree, and if I removed all these vertices, so imagine I remove this green and the red vertices completely. So in the subtree subgraph that I have, obviously it will be a disconnected graph, any subtree I find, okay, and if I look at the neighbors of this vertices in the subtree that are not part of the subtree, that are outside basically, they can be at most 2 of them. Basically you can have one edge coming in to the, so this is, if this is a subtree, this is also would be a rooted subtree, right. So there will be an edge coming in, connecting to the root, and there will be one arc actually leaving, at most one other arc leaving this subtree. That's what basically this says, at most 2. Okay, so now you know some useful things. So now I'm going to describe that guesses, what that meant by guessing the structure of the upset vertices, the affected vertices, okay. So suppose this is an SBA. I know this is the hypothetical SBA. So my favorite here is denoted by V star, okay, because just lack of space and so on. So the yellow vertices are the affected vertices, okay. So I'll say affected vertices. And these blue vertices are the least common ancestor vertices. See, between this yellow and yellow, this is the least common ancestor, right? So between this and this is actually the ancestor of this. So between this and this guy itself is its answer. It is the ancestor of these two things. So this is trivially true. So between this guy and this guy, the least common ancestor is V2, right? So that's the thing. And we always add our favorite to the affected set, like just sort of a reason. Okay, so this is suppose the SBA that we are trying to find, that we are given, okay. So from here, what I do is, if you notice, I am going to compress all the edges basically. So from V star, I look down, okay, and I try to find a path so that beyond that, there does not exist any yellow vertex. So did you follow what I said? Starting from V star, I look for a path and I stop where I cannot find a yellow vertex beyond that. Can you point out one such thing? See this path, V star, V2, V4, V10. Beyond this, there are no yellow vertices, right? So this is the part that I compress first, okay? Okay, forget about compress, I say delete it, okay? So because beyond this, there are no yellow vertices. Similarly, here also, I can sort of delete, I'll use maybe a cross, it's easier, okay? What about this? Well, here obviously there is a yellow vertex, and beyond this yellow vertex, there are no vertices. So I basically stop here. What about this? Well, it turns out beyond this V2 guy, there are no yellow vertices. So basically, I get rid of this as well. Correct? Okay. So, and I do this here, and V9 is gotten rid of. What about V14? Well, the same thing. Now, notice, why did I not get rid of V7? In this step, after I got rid of V14, why did I not get rid of V7? Because V7 did not just lead to V14, but it goes all the way down to V17, which is a yellow vertex, right? So these are the things that if I got rid of, this is the situation that okay, not yet. So this is what I do in the first case, okay? So I just get rid of all these truncate paths, basically, beyond which there are no yellow vertices to be found. Now furthermore, what do I do is, I go again back to the root, and I go down to a blue vertex or a yellow vertex, one of these colored vertices, okay, and I see if there are no colored vertices in between, then I can sort of compress that path also. So for example, between V1, V star and V3, this is one uncolored vertex, so this path can be compressed, okay, into one arc. So similarly, between V3 and V17, now I do this not just from the root, I do it from all the blue vertices there onwards, okay. So between V3 and V17, there are these uncolored vertices V7, V13, okay, and I sort of get, I compress this path as well. So that is why V star has a child V3 after this compression. Basically, V1 is gotten rid of and V3 rises up. V7 and V13 is gotten rid of, so V17 becomes now a child of V3. Okay, so that's what is happening here. Similarly, here I basically get rid of this thing and V15 becomes a child of V3. And I do this, this is what I get. Okay? Yeah. Least, yes, yes. So I should probably mark this. Can you see this? Yeah. So affected vertices are those upset vertices, okay? So I just use them as a LCA. These vertices. So X are these affected vertices, and so let's call this as X. What's going on? Okay, yeah. So this is the thing. So blue vertices are those which are not in X but are part of the LCA closure. Okay, so this is what I get after compressing all these things. Now the next step that I do is I actually remove the labels of the blue vertices. This is what I call the template of this tree. This is template what? I think I chose a different pen maybe. Yeah, this is template, okay, of X in B. Sir, so yes, see the number of vertices in T delta and T star are the same. The T star has a few labels missing, that's it. Now from the previous property, what we saw was that if I only looked at the X vertex and its LCA closure vertex, right, that bigger set is at most twice the size of X. So this is a subgraph of this. The number of vertices here can be at most 2 of X, meaning there cannot be more blue vertices than there are yellow vertices. Okay? Yeah, so it's not a subgraph. So I just mean, sorry, that's actually incorrect. It is not, okay. So the thing is, it is not a subgraph if you think of the original win-lose graph, right? Because the yellow vertices, I don't know the relationship, like I don't know what is the relationship between V star and V15. Is the arc sort of, is there a, okay, this is not a good example. Let's say for this case. So between V3 and V17, I know this arc actually exists in that graph. Why? Because V3 is not an affected vertex. So it means that this edge, if it is going down, also exists in the original graph, meaning this is not one of those those edges. So this is fair, meaning you can infer some of these things, but the information that I'm missing is I don't know, for example, how do I say this? Okay, in this. Yes. Transitivity, I can infer some of these relationships, yes, you can say that but this is not, so the fact that these edges exist means that you can infer these edges exist in this original graph. in that original win-loss graph, because the original win-loss graph is a tournament graph and it has this nice transitivity properties, for example. So anytime you have an edge, you have this relationship between the white vertices, for example, from V1 to V7, you know there exists an edge between V1 and V7. Okay. So if, for example, okay, this is the example. So between imagine there were other vertices in this path. Okay. So when I'm compressing this path, okay, when I'm sort of getting rid of this and getting this sort of situation where I'm basically V3 to V17, I know this edge does exist in the win-loss graph. So it has, I have to be a bit careful as to because there can be some back arcs and so on and so forth, but some of these edges do exist. Yes. Right, correct, but I completely got rid of all the white part. So I'm truncating between, say, V3 and V17. So this edge exists in the graph. Yes. So between V4 and V10, of course, this edge exists in the graph because this edge is between, so see this V4 and V16, right? So, okay, this is a particularly bad example in which we cannot sort of see, but imagine a situation where there were sort of edges going, there were more yellow vertices here, and I got this compressed edge by basically truncating things, so on and so forth. So, because these are yellow vertices, they could be that the relationship is opposite. I think that could happen. Okay. So what will happen is when I will add these edges, it's like V4 will never have to play V10. V4 will play somebody else and that person will play somebody else and so on and so forth. Okay, I will just think about what you asked and just answer offline. Okay, so now, okay, just to go back here. So what did I do here? This is the type of information that I'm going to be guessing. I know the affected vertices. I don't know the identity of the LCA closure vertices. I don't know these vertices. I know VF, I know my V star, okay. I don't know this, what is it? These. So the people who are part of the LCA closure but not part of the affected set, precisely these blue vertices. I don't know the identity. They exist, but I don't know. So basically, I will be guessing this structure entirely. These blue vertices are like placeholders. When I know that who this person should be, I will be placing them. That is what happens in the third step. Okay, so this is the guess part. Furthermore, what I'm going to guess in the thing is that when I guess this structure, this is only a partial structure. This is supposed to mimic this hypothetical solution that exists. So what I'm also going to guess is the length of this arc in that actual solution. I will also guess these sorts of length. What is the actual length between, these are arcs in this template tree, but in the real solution, they are basically extended paths and so on, okay. Similarly, I will also guess maybe there are subtrees underneath this and so on. Because this is an SBA, one of them has to be a single vertex, this is, and so on and so forth. So all those relationships will be verified in the second step. Okay, so I also guess the size, okay, the size of V star is known to be n because that's the root. I also guess the size of the subtree rooted underneath this, size of the subtree rooted underneath this. All this information is part of my guess template. So, okay, so let's just move on. I have explained what this means. Now, the question is, this guessing means what? I'm actually enumerating all possible such templates. That's what guessing means. Now, there is a famous result by Cayley. It's a well-known thing that on n vertices, the number of rooted label subtrees you can have is n to the power n minus 2. Okay, so using that, our n here would be x, that's set x, VF, the affected set, so that is size k. So basically, if taking x to be k, we can guess the all possible templates in this much amount of time, k to the power order k. Okay, this is just application of this formula to the fact that x is k. Okay, so this is the amount of time I'm going to have to spend in guessing the possible templates. Now, if you look at this closely, this can be written as k log k. So this is where I have already spent that exponential amount of time, this much of guesswork. Now, after I am done with this, Then I'm going to, so these are all these things that we guessed, and now I'm basically going to, so what does it mean to basically guess the length? It means that, well, I'm going to find a length function. Basically, it will take each of the arcs in that template tree and basically tell me what the, how sort of large the length of the arcs should be, like how much they need to be expanded to get the original tree. So this is basically a path, this is a function from 0 to log n. And for the subtree, you, for the tree case, you basically guess 0 to 2 to the power log n. Okay. So now, once I have guessed this thing, I basically, let's see how this thing happens, because now I'll be moving to the next step, okay. So this is the guessed situation, this is the relationship, this is my favorite guy, favorite player, followed by F, followed by A. This is a path whose length has been guessed to be 2, okay. So now, basically I have to go back to the win-lose graph and find 2 vertices that can be placed in here, so that these edges, okay, have these edges, because I need a rooted tree that is always pointing downwards. So these edges actually exist in this graph. This is what is going to happen next. So this, I need to find 2 vertices to place in this path, so that I get one long path between this guy to this guy, okay. So if I see, and similarly for this and this, let's say I have guessed the length to be 1, and this is again length 2, then I can see that, okay, this is size D and so on and so forth. Okay, this was just a running example. Then, okay, I'll just rush a little bit. So this is sort of the thing that I guess for, this is one whole, a template, length and size, okay. Now, the next step is basically to find, okay, so these are just some definitions that you don't sort of need. So suppose I find, I'm able to test that those guesses can be part of an SBA. So for example, what I mean by that is, suppose this size, okay, these are both sort of and children of this guy in the template tree, right? So they will become descendants in the eventual solution. If this size and this size cannot be, because SBA has that property of the power of 2 and so on and so forth, if those sizes don't make sense because they are part of the bigger subtree rooted at this vertex, we say this guess is invalid. Okay? So basically we look for a template that can be extended to an SBA. That's what happens in the second step. And then, so this is what the realizable step is, that the thing that we guessed can actually be extended to an SBA. This is actually a polynomial time test. Basically, you are doing a DP to see if the sizes and the values sort of match up and so on. Okay. So this one takes, so the reason I am emphasizing in all this time complexity is like to show you how I get to the 2 to the power order k log k polynomial n time. Over here, I only use polynomial amount of time, and then now comes the sort of the main meat on the bone part, where basically how do I find those internal vertices, okay? So this is a path, this is an arc that exists in my template tree. I have guessed the size to be 2. So what I am going to do is basically, in order to resolve this path, I basically need to add these internal vertices. So how I do that is basically roughly this, okay? So there are few details involved, but basically this is what is happening. I look at where U and V sit in that topological ordering, what is this thing is. Now U in this case will be, so who are the vertices that have a label in my template? These are the affected vertices, correct? So this is an affected vertex, this is an affected vertex. So I start with this affected vertex, I go up the tree and look for the first affected vertex I can find. So this is like the path that I'm going to fill out now. Following this, I basically look for a subset of vertices, the highest ranked vertices of this much size, this many number of vertices that lie between U and V. So if I've already used some vertex, then I cannot reuse it here. Whatever available vertices I have, I pick the highest of them of this much size, and basically place them in this path. Okay, so that's basically the path resolution thing. So if you look at that example, then basically this is what would happen. This is internal vertices are 2, so you will add some number of, okay, this should be actually 3. This should be 3. Okay, so yeah, so it should be ABC. Okay, so this is how I resolve this thing. Now the question is, why should this actually lead to a solution? That actually requires a proof, and I'm horribly out of time, so there's no way to explain this. But the main idea was to say that if just by knowing the structure of these affected vertices, which are the upset vertices, among each other, like who is an ancestor of whom and so on, I could actually deduce the relationship or the position or the matchups of all the unaffected vertices, just by basically looking at the topological order and finding vertices to basically place in them. So that's basically the idea of the algorithm. So now obviously there's another step where basically I resolve the subtrees. I fill out vertices appropriately into the subtrees because I have also compressed the subtrees, but they also only consist of unaffected vertices and so on. So I claim to you without proof that all of this can be actually done. Okay, so have you all seen greedy algorithms before? Have you all seen? So usually the point is to show that, okay, suppose there exists an optimum algorithm and you have a greedy algorithm. So if your greedy solution differs from the optimum solution, okay, then there is something you can do to the optimum solution, like you can make some changes, okay, and then by making, it's broadly called an exchange argument, your optimum algorithm looks similar to your greedy solution without actually change in cost. So here we do not have a cost notion, we just have the notion of there exists an SBA. So this proof basically goes forward as saying, okay, this is what my greedy algorithm does, but optimum has some other way of solving this problem. A tree exists there and here. Why is it different? Suppose I make some changes to there's a way of changing the optimum solution which looks more like my greedy solution, and yet I do not destroy the structure of the tree. So we do this step by step, it's an inductive proof, and so basically that's how these sorts of things happen, that every time I can sort of make some adjustment and make the optimum solution look more like the greedy, and so therefore, in other words, saying like the greedy, if I do this n number of times, basically then the optimum looks exactly like the greedy, and then basically the greedy is a valid solution. Like the greedy algorithm would actually lead to a solution, okay? So here you don't have an opt, but there exists a solution which solves this problem because there is no cost involved here, right? Yeah, I don't know why we call it opt, but yeah, that's the thing. Okay, so this is, I was never going to sort of get to the subtree resolution thing, but I think I can stop here now and sort of ask you to maybe ask some questions if you have.